Good morning. I'm Renati Rennie, the president of the Tinker Foundation, as Peter said, and it is my great pleasure to be here today to personally present the 2016 Tinker Muse Award to Professor Robert DeCanto. It's also great to be here to see so many old friends from the Antarctic field, because my field is Latin American Studies, and so I made many new friends when we started working in the Antarctic, and I'm glad to see them here today. For those of you who don't know about the prize, I'd like to read a few sentences about it so you know why it is awarded and why it was actually begun. The Tinker Muse Prize for Science and Policy in Antarctica is a $100,000 unrestricted award presented to an individual in the fields of Antarctic science or policy who has demonstrated potential for sustained and significant contributions that will enhance the understanding and/or preservation of Antarctica. The prize is inspired by Martha T. Muse's passion for Antarctica and is a legacy of the International Polar Year for 2007-2008. Now, as many of you may not know, Martha Muse died a couple of years ago, so I'm really happy that this legacy exists in her name. This prize has been awarded annually since its inauguration in 2009, and Dr. DeCanto is the 8th recipient. Each year, I think that it is impossible to select an awardee as accomplished and as qualified as the previous ones. They have all been really great, but each year I am proven wrong. Before I present the award to Dr. DeCanto, I want to express my sincere appreciation to the team at SCAR, especially Owen Griffin, and to the selection committee, led this year by Professor Peter Barrett. The committee members, as was mentioned, spend many hours evaluating the applications, and given the quality and quantity of the applicants, this is no easy task. The Tinker Foundation is fortunate to have such dedicated scientists who are willing to join the committee year after year. Again, many thanks. And now to the award. This year goes to a world leader in the study of Antarctic climate and its dynamic and vulnerable ice sheets. He is an acknowledged leader in his field, generous with his time to colleagues and students alike. It gives me great pleasure to acknowledge his many achievements, past, present, and of course, future. Professor DeCanto, please. I'd like to... This is a symbol of the ice in Antarctica, and I hope it will never melt. And also a little check for Dr. DeCanto. Thank you again, and congratulations.
Considering my reputation, I better get started. There we go. Okay. So I don't know how many of you saw the film Ice in the Sky a few days ago. It was really inspirational, and I sort of framed what I'm going to do today around a quote that I heard early in the film, and it's written here: "The people without whom I could not have done anything." Okay, so I'm going to take a little personal sort of timeline journey through some of the science, and it'll give me a vehicle to thank some, certainly not all of the people that have impacted the research, myself, my thinking, my science, and in my career, my fun, all of it. And it does start with Bill Hay. Bill, I think, is largely underappreciated. He was really one of the first American geoscientists, a pioneering paleoceanographer, I think initially a micropaleontologist by training, but so broad in his thinking. Bill was one of the first people to think of numerical models, climate models, that were just beginning to come online at places like NCAR, at the big national labs, as potential geological tools. So it was really great timing for me to take a class for Bill after he had come from Miami, the Rosenstiel Marine and Atmospheric School, to Colorado. I took an oceanography course, and it changed my life, literally. There were some pauses, as Peter noted, and spent quite a bit of time in the south of France, climbing on limestone, but you know, a lot of us in this community are passionate about the outdoors. A lot of us were outdoor athletes when we were young, still are, and you know, that's a link that I see running throughout our community. So Bill helped get me set up at NCAR. University of Colorado at the time was growing in atmospheric and ocean science, so I was able to get a solid background in ocean dynamics and atmospheric science and classical glaciology from Mark Meyer, who at the time, I think he founded the glaciology program at the USGS and was an expert on tidewater glaciers. And it's funny because some of the things that, reflecting back on courses from Mark, have just suddenly recently impacted what we're doing with the ice sheet models today. So another really amazing piece of luck for me is that when I was at NCAR as a graduate student and later a postdoc, it began in trying to understand the dynamics around times in the past when the world is warmer, how the poles can be so warm in the tropics not to burn up. So these were, you know, more atmospheric dynamical problems. But Dave Pollard had been pulled out of industry, back into science, and was at NCAR basically doing code development. So he was doing atmospheric model code development, and I was in his section at NCAR, and I was using some of the tools Dave was working on, so he was my go-to guy. And I started to hear about Dave's sort of previous life, doing some pioneering work in using simple climate models coupled to very simple, like axisymmetric ice sheet models to try to understand glacial interglacial cycles. And I thought, well, that sounds cool. I know a little bit about ice from Mark Meyer, and so sort of on the side over the course of years, even though we were both supposed to be working on different things, we just started talking about ice a lot. Dave started tinkering with very simple two-dimensional shallow ice approximation models, and it came to the point around the time that I had finished my degree. I was in a postdoc. Dave left NCAR. He went to the East Coast, to Penn State. I stayed at NCAR. At that point, I was doing ocean modeling. But we thought, if we should someday write a proposal, because we were beginning to learn about records like this, people like Jim Zakos, paleoceanographer, creating these incredible records of these remarkable events in Earth history. And, we had to think about, in this case, the remarkable transition from the essentially ice-free world shown here in this isotope record across the Oligocene boundary, when Jim was pointing out that it looks like the Antarctic ice sheet grew really suddenly. It looks, this is a dramatic transition. It happens very, very quickly. So, right, with this background at NCAR and working with numerical models, well, what could numerical models come to bear in a problem like this? So the first problem was that GCMs, climate models that we were working with at the time, they didn't have an active land ice cryosphere component. You didn't have a dynamic ice sheet model in the GCMs back then. So we thought, well, let's write a proposal and try to develop one. And that way we could potentially study events like the Eocene-Oligocene transition. So that's what we did. And we thought, well, if we can start to develop models, we can start to compare the model results with geological records that can then potentially feed back on the climate modeling we're doing, potentially improving the modeling. And that ends up, being sort of the foundation of what ACE and PACE, some of the SCAR programs are about, linking the modeling with the data. So as we were beginning to advance in the modeling, extending a very simple 2D shallow ice approximation model to 3 dimensions, these are the kinds of people that we were leaning on. So we were borrowing heavily from people like Catherine Ritz, the numerics in her shallow ice approximation model of Greenland, borrowing heavily on that, and then coming up with techniques of actually coupling the climate model with an ice sheet model. And the first thing that we started to do is to think, okay, so these problems evolve over timescales that are relatively quick for geology, but they involve orbital timescales. So these models have to be able to simulate orbital cycles, multiple orbital cycles. So the things that we began to do is develop ways to sort of speed up the simulation so you could run climate ice sheet simulations through multiple orbital cycles And what we started to do were things like this, just sort of arbitrarily, okay, let's run the model with 2 times present-day atmospheric CO2, so 560 parts per million CO2. And what we found was ice volume jumps up very quickly. We grew an Antarctic ice sheet very suddenly. And then we realized we could do things with the model mimicking changes in plate tectonics and ocean gateways, changes in ocean heat transport. And what we found was if CO2 is low enough, you can do a lot to the Southern Ocean, and it doesn't change the model results. You're going to grow a big ice sheet on Antarctica regardless. At very high levels of CO2, we weren't able to grow an ice sheet, maybe just little ice caps on the highest mountains. And you could cool down the Southern Ocean as much as you wanted, and you still weren't going to push the system over the edge and grow a big ice sheet. But we were finding that there were these sweet spots in the middle. We could identify ranges of CO2 where, lo and behold, the changes in the Southern Ocean temperatures made all the difference. So we were beginning to see threshold behavior in these models, but one thing that we were lacking at this point was that CO2 wasn't changing in any of these simulations in the early work we were doing. So people like Mark Pagani and Paul Pearson in the UK were developing pre-ice core era CO2 records. And what those data were suggesting was that, okay, and I think you know the story, that CO2 driving, the ice-free conditions of the early Cenozoic dropping through the Cenozoic toward the sort of pre-industrial levels we have today. So we needed long transient simulations with CO2 going down with the orbital forcing sort of superposed on top. And that was the next big advance for us, was coming up with techniques to actually do that, where we have CO2 and the orbital forcing. And that resulted in the paper in 2003 that Peter mentioned. And this just looks so crude now compared to what we're able to do. Here's CO2 gradually going down very, very slowly with the orbital forcing superposed on top. And what we found was eventually the individual ice caps on the high terrain touch, buttress, ice sheet surface goes up higher into the atmosphere. There's this positive geometric feedback, and you suddenly trigger the growth of a big ice sheet. And the way that looks in terms of volume, as time evolves, low ice volume, little wiggles in the ice volume, that's the orbital forcing, and then that's a big transition as the ice sheet grows suddenly. And it's growing suddenly in response to incredibly slow atmospheric CO2 forcing. It's a threshold. It's a nonlinearity in the climate system. And when years later, this was fantastic. New records were coming out, isotope records across the Eocene-Oligocene transition. And of course, these oxygen isotope records are a combination of ocean temperature and ice volume, but they even looked very similar in shape to what the model had produced a few years before. And what was really encouraging was that as new CO2 records across the interval were being developed, we realized that the climate ice sheet model actually triggered the growth of the ice sheet at about the same level of CO2, maybe 700 parts per million, that the geochemists were telling us existed at the time. So this was a really pretty fun success, and what was neat was that we were blind as to much of the data that came later after the modeling. So we began sort of applying the same sort of techniques to the northern hemisphere, getting a feeling for the threshold of CO2 that it would take to grow ice sheets in the northern hemisphere. Of course, those thresholds for growing big ice sheets in the northern hemisphere are much lower than for the Antarctic. But, it didn't take us long to think, okay, well, we're probably going into a future with high CO2, much higher than today, potentially even surpassing the CO2 levels that it took to grow the ice sheet in the first place. So what's going to happen to the ice in the long-term future? So we began the first part of at least my career trying to grow the ice sheet. That's the birth part of the story. And the next 15 years, 12 years have been spent trying to destroy it with the models. Okay, so I was introduced to a lot of the community that's in this room at this meeting. This was sort of the end of the SCAR Antistrat research program. They had their sort of culmination meeting in a beautiful place. The Antarctic community likes to have meetings in the best places around the world. So I was happy to be involved. here are some of the cast of characters. And already at that meeting, we were beginning to sort of sow the seeds for model data interaction and what would later become the SCAR-ACE and later SCAR-PACE program. People like this, David Harwood. David, you know, I was learning about diatoms, and he was telling me about sea ice diatoms, and he knew we were growing these ice sheets on Antarctica, and he kept saying, Rob, what about sea ice? Is sea ice really important to the story? So this is the kind of, you know, this really fantastic, just personal interaction in relaxed settings, often a glass of wine or beer involved, leading to new research, new science, thinking about new ways to look at the system. And so what we did with David, from his inspiration, was to just look to see, as you slowly, gradually drop CO2, what happens first? Do you start to grow a lot of sea ice in the Southern Ocean, or do you start to trigger land ice growth first? And what we found was, as CO2 is coming down, you trigger the big growth of the land ice, and as the land ice expands, the southern sea ice grows. And so that was kind of a neat, you know, recognition that, wow, you know, the threshold for growing land ice on Antarctica actually probably came before the sea ice, and that the sea ice is somewhat of a slave to the growth of the land ice. At the same time, the development of the southern ocean wind field completely changes as the ice sheet grows. We had that recognition, and with that, as the catabatics and the easterly outflow off the continent spin up and we still have strong westerlies, you know, we started thinking about, wow, what's all that divergence going to do in the Southern Ocean? And to think about biological turnover and impacts on the ocean carbon cycle. So really great. It became very quickly very interdisciplinary, and which just made it more and more fun. And right, so I had gone from learning about geology and geophysics and the atmosphere and the ocean to the cryosphere and the modeling, and now I was learning about ecology and biology. Fantastic, really great, fun. Okay, so spinning off of this, this is the workshop Peter mentioned. We thought, okay, Antistrat is over. What's next? We were beginning to see the seeds here, the potential for more model data interaction. And so I held a workshop close to my home institution in Massachusetts. It was funded by Scott Borg, who was initially, right off the bat, really supportive of getting the modelers communicating with the more data side of the community. And that workshop report ultimately led to the foundation of SCAR-ACE. And as you know, ACE was a long-running program, highly successful, generated a lot of high-impact articles. The initial co-chairs of ACE were Rob Dunbar, and I just want to thank Rob publicly for winning the Excellence in Antarctic Research Prize. Congratulations, Rob. And the former Muse Prize winner, Martin Siegert, and they did a great job handling the early era of SCAR-ACE. Around this time, you know, I had opportunities to get into the field, and that completely changed my outlook again. And, you know, now I am so proactive in trying to get my own graduate students and postdocs to get out into the field, any opportunities to get to Antarctica, to get on the ice, to do work. Now, ideas were brewing to sort of resurrect sort of the glory days of geological drilling around the Antarctic. And here are some of the cast of characters that were trying to bring back geological drilling to the Antarctic region. Tim Naish, Peter, who had a long history, of course, in geologic drilling around the Antarctic margin, the Wilson twins, Jane, Dave Harwood, Rich Levy. These were really the heroes of the development of Andrill. And what was really, I think, unique about Andrill is that in part through Scott Borg's encouragement and NSF, the modeling component, you know, we could see what modeling could potentially bring to this. It wasn't going to be this sort of ad hoc thing where they were going to write an Andrill proposal and I was going to go home and write a sort of loosely linked proposal to do some modeling. We combined forces and we wrote an integrated science program and proposal, really thinking right from the beginning as to how the modeling and the potential records that were going to come from Andrill could be woven together. Now, this posed a really important problem for us, and the problem was that they were going to drill through an ice shelf and try to say something about the long-term history of the Ross Sea, the ice shelf coming and going, maybe the grounding line overriding this location. We didn't have ice shelves in our model, okay? So this was a longstanding problem, a difficulty in having a continental scale ice sheet model that includes the grounded ice up on the continent and the floating, stretching ice flow of the ice shelves, and the dynamics, the coupling between those two systems, the buttressing, the marine ice sheet instability physics. And it was really, it was sort of the breakthrough of Christian Schoof, and meeting him at EGU, and I think 2007, when he was publishing these papers, very careful boundary layer analysis of the grounding line, Christian was able to give us sort of a scaling of how much ice should be going through a grounding line given the thickness of that grounding line. And wow, suddenly we had a way to parameterize the amount of ice going through the grounding line from an ice sheet out into the floating ice shelf, instead of having to have very super high resolution and very complicated numerics. And this let us have models that could simulate long geologic time spans, but included the dynamics of the coupled ice sheet ice shelf system. And this is an example of just the last 400,000 years of this model. So this was a big step for us. So we were now able to sort of simulate the environment in the Ross Sea and the whole broader continent at the same time over geological length intervals, and potentially compare with the records that were coming out of the ground being produced by Andrill. And as you know, Andrill's 2 seasons of drilling recovered remarkable material spanning about the last 15 million years. The first core had a beautiful last 5 million year long record. And as Tim Naish and his colleagues were trying to decipher the meaning of those results, we got together literally in my kitchen, spent, I think, about 5 days, like hardly going outside. And you see Dave here. You know, this was the real core of it. This is how we were doing it. We were writing the papers like this, literally working late into the night, right? Evidence of the Chinese food and empty wine bottles. And that kind of just passionate but relaxed collaboration produced these 2 companion papers in Nature, where we were able to really link the modeling with the data. In fact, actually producing a synthetic sediment core at the drill site where we could actually link specific retreat and advance cycles of the West Antarctic ice sheet to what they were saying in the geologic record. And one of the important outcomes of that work was the recognition that at least as recently as marine isotope stage 31, just over 1 million years ago, it looks like the Ross Sea was open water, relatively warm, high productivity conditions, very little, even drop stones from sea ice, really dramatically different environment just 1 million years ago. We don't know if events like that could have happened more recently in the geologic past, where we need more records like this one, for example, of the last interglacial. So Rob and Martin stepped down as co-chairs of ACE, and Carlotta Escutia, really, really dear friend now, and I took over. And and I will just mention that Carlotta, right, she was a champion, a co-chief of a very important Southern Ocean drilling program expedition off of the Wilkes Land margin that was producing remarkable records of what appeared to be, for one example, pretty dramatic Pliocene variability of the East Antarctic ice sheet. Now, we've turned our attention from the West Antarctic ice sheet to the East Antarctic ice sheet. One of the first things that we did as co-chairs was to run a meeting in Grenada. Carlotta did the bulk of the work. I helped with the scientific program. This was fantastic because one of the eye-opening things for me, more interaction with a broad community at this meeting, was the introduction to, and now we're very close colleagues and friends, Maureen Ramo. Maureen came to the meeting because she was becoming more involved in the community that was trying to reconstruct ancient sea level. And she was getting at it from 2 different angles, looking at changes in the chemistry of the ocean and going out all over the world trying to find outcrops and ancient beach deposits and mapping them, and then using GIA and other geophysical techniques to kind of reconstruct their position at the time they were deposited, to say something about ancient sea level. Now, what Maureen and her colleagues and other people in this room have worked on Pliocene and Pleistocene sea level problems, one thing that we were learning was that the models were not producing the range of variability that the sea level records were indicating, or the sorts of records that were coming from Carlotta's ODP expedition, on the Wilkes margin there, that red dot, Site 318. So this posed another problem for us on the modeling side. So here's another example of geological records driving the model development and the model physics. It made us rethink the model that we had and what might be missing. The first thing that we turned to, and I talked about this yesterday, was the potential influence of surface meltwater driving the collapse of buttressing ice shelves around the continent. So we added physics to the model to account for that, events like the Larsen B breakup, for example, in 2002. And what we realized that if you had a nice, healthy ice shelf buttressing the flow of ice from the continent out into the ocean, if that ice shelf were to hydrofracture because you had a lot of surface meltwater on top of it, you could end up with a situation like this, where you have a very thick grounding line in contact with the open ocean, and if that grounding line is thick enough, let's say a kilometer thick, then you could have a very tall subaerial ice cliff that might be inherently unstable. And that instability in that ice cliff face wasn't really on our radar so much as the hydrofracturing part of the physics were, but really through inspiration by people like Richard Alley, who, he had spent so much time looking at where ice reaches the ocean, forming a cliff, and looking at things, parts of the Antarctic margin, the scale of like the Thwaites terminus, for example, the Thwaites Glacier terminus. David Vaughan was thinking somewhat along the same lines. And they were, I was talking a little bit to David Vaughan and Richard and Dave Pollard, were our colleagues at Penn State, and it sort of sparked something in us to, think, okay, let's add those physics, a mechanically collapsing ice front in places where we have very, very tall ice cliffs after we lose buttressing ice shelves. We added those inspired physics into the model, and for the first time in 10 years of trying, we were able to start to simulate the kinds of sea levels that the geologists tell us existed in the Pliocene, in the last interglacial, in other geologic time periods. So this was great. It felt like, okay, now we might be onto something. Now this has really important implications for the future. What happens when we take this new model that is now finally able to reproduce some of these paleo-ancient sea level rise events into the future? So in the more recent past, last few years, this is where the research sort of state-of-the-art for us is. We're developing some new large ensemble techniques to actually use the geological data in a statistical, in a quantitative way, to really tune and get at the fine-scale tweaking of the model physics before we start to run future simulations. And having done that, and then recently publishing the results of what happens, Peter alluded to simulations like this, where these are ensembles of future CO2 scenarios following the standard IPCC RCP scenarios here over the next 5 centuries out to the year 2500. And what we found was in scenarios with very aggressive mitigation strategies, the so-called RCP 2.6, where in around the year 2020, 2030, 2040, we start to tail off our emissions, and by the time we get to about 2080, we've gone to net negative emissions. We're actually pulling CO2 out of the atmosphere. Almost nothing happens to the Antarctic ice sheet. We get very little sea level contribution from Antarctica. Now, this doesn't include contributions from Greenland or ocean warming or other effects. This is just the Greenland or the Antarctic piece. But, what was a little bit scary is that in scenarios with very high sort of business as usual greenhouse gas emission scenarios, it's a really different story where we are simulating up to as much as a meter of potential sea level rise coming from Antarctica alone on the course of a sort of century time scale, which is a somewhat different results than some of the other groups we're getting. And again, right, these model physics, we're not using any model physics that do something crazy in the last interglacial to Pliocene. So, this is where we're going. It's still all very loosely constrained, and we need more data, and we still need better modeling tools, but you can see where we're going, and we'll continue to refine work like this over the coming years. But this reflects potentially the role of policy, and I see this as a really nice link to the spirit of the Muse Prize, right? This is about both the science and the policy. Okay, another important recognition is just, this, and this is what sort of the more modern simulations look like. This is the ice sheet grounding line is the black line, and these yellows and reds are showing melt on the surface of the ice sheet. So one thing that this new work is suggesting is that we've been really focused on damage to the ice sheet by melting the ice shelves from below, by ocean warming. We need to worry about what's going on in the atmosphere too. And there were really great sessions on the first day of this conference looking at interannual variability. When is the timing of potential big meltwater events going to begin to appear on the big ice shelves? We might need to be worried about that happening. Okay, and then sort of to wrap up, so even more aggressive and transformative than an RCP 2.6 future scenario, people have begun to think about, okay, maybe we really need to get our act together here and do something even more aggressive and dramatic in terms of reductions in emissions and maybe even some geoengineering to get greenhouse gas levels under control. What does a 1.5 degree world look like? We're almost there today. This year, I think from January to last month of this year, if you look at the global mean average, I think we're over 1.3 degrees warmer than pre-industrial. Okay, so we're flirting with that 1.5 degree warmer world already, but let's see what the world looks like at 1.5 degrees and at 2 degrees. And those were the sort of target numbers that were discussed during the Paris climate talks a few months ago, 1.5, 2 degrees. Okay, now the problem with that is that if you actually add up all the commitments, the so-called INDCs, these are the intended nationally determined concentrations, what every nation is really going to commit to. If you add the current agreement up, it gets you to about 3 degrees of warming by the year 2100, not 2 degrees, not 1.5 degrees. So we thought it would be interesting to see what this new model that has been geologically constrained now does at 1.5, 2 degrees, and then what the real INDCs do. And you can see what 1.5 and 2 degrees do, not much. Good news. But the current concentrations that were discussed at Paris, getting us to something closer to 3 degrees, not such good news, suggesting that maybe that's not even good enough, and we need to do even better. So we really need to figure out whether or not there's some threshold in the system between 2 degrees and 2.7 or 3. Is that a real threshold? Is it much higher? Is it even lower? And again, right, you can see that I still and Dave and all of us have plenty more work to do. Okay, I think Martha Muse would be really pleased to know that just last week in Geneva, among a very select group of people, there were 3 Tinker Muse Prize winners at the scoping meeting for the next special report by the IPCC that's actually looking at a 1.5 versus 2 degree world. Myself and Valerie and Tim Naish were all at this meeting. This is the first time a report will be written that's combining all 3 working groups of the IPCC. So you've got the physical scientists and you've got people studying mitigation strategies, energy policy, and social science all in the same room. So it was a very exciting time. There's a lot of optimism that we can get to 1.5 or 2 degrees. But we need better modeling if we're going to say something about what the world looks like at 1.5 versus 2.5 degrees. There's still an unacceptable amount of uncertainty. Okay, and toward that end, where ACE has gone is it has evolved into a new program at SCAR called PACE. Carlotta and I helped facilitate getting that off the ground, along with another cast of good, close friends and colleagues. And this is sort of the next level of integrating modeling with records, both up on the continent itself, in the continental interior, out into the deep sea, even the tropics, telling us something about sea level, and then bringing the GIA community, the geophysicists and the geodesists who help us reconstruct sea level into the fold, with the eventual hope of refining the modeling over here so that those future predictions get even better. So now that SCAR PACE is off the ground, it's time for new leadership. So Carlotta and I have just recently stepped down as co-chairs, leaving the program in the very capable hands of Tim Naish, former Tinker Muse Prize winner, and Laura DeSantis, who is now, we've just heard, has been announced to be co-chief of a new drilling leg in the Ross Sea in the Southern Ocean. So congratulations to both of them. We know that PACE is now in good hands in their first task, and I wanted to get this up here because I want you all to get this into your calendar. Very exciting meeting. We're hoping to encourage some of our more interdisciplinary colleagues, whether you are in AntClim 21, Antico, you're an ecologist, you're thinking about the evolution of genetics of different groups in the Antarctic. We are hoping that you all attend this meeting in Trieste. It's going to be a fantastic venue, so put it down in your calendar. And then I'll just finally thank everyone. There are way too many people who have influenced the science along the way. This was just a little glimpse of, the interaction, the collaboration. I know there was a lot of alcohol in most of the photos, but it's, I think it just kind of demonstrates the joy, really, in the discovery, in doing the science. And it has certainly, I can't think of a better group of colleagues or a different career path that I would ever choose at this point. And so I thank you all for contributing to my joy and my pleasure. The science is serious, but it has also been very, very enriching from a personal perspective. So I'll thank the Tinker Foundation, Martha Muse, and the Muse family. Of course, the selection committee for selecting me among, I'm sure, a very talented pool of applicants, and I'm very honored to be among the people that have already achieved this award. So thank you very much.
We'll just be polishing off with some photographs, but please stay around for the following session, which is going to be on the SCAR and COMNAP fellowships, and that'll be after we've rearranged the stage. We'll be following directly afterwards. Thank you very much. Okay, so the following mini symposium on the fellowships will be right in this room, so just stay still for that. Thank you.
this symposium.
So this is the first.
It's not going to.